Hello. So today we'll go through one of the questions is related to design a pump and how can we select the right pump for this design. This is an example from your textbook. The textbook I recommend for this paper, Advanced Fluid Mechanics, Applied Fluid Mechanics by Robert L. Mott. I recommend if you get the 6th edition. If you like really fluid mechanics, I strongly recommend you buy this textbook because it's really good and helpful with many of the equations. The textbook also provide you this file, which is an Excel sheet, and we can embed all the equations we want to solve and how can we address them in a way to go through them by filling using equation editors. So let's start with the following example. A system in which a pump is required to deliver at least 850 liters per minute of water at 15 degrees Celsius from lower reservoir to an elevated tank maintained at a pressure of 240 kilopascal, which is the P gauge pressure. Design the system and specify a suitable pump, then determine the operating point for the pump in the system you have designed and give the performance parameters for the pump at the operating point. Very good question. And also is giving you the Q meters cubic per minute, which we need to convert them to meter cubic per second. And then that's the HA calculated. And 0 when it's saying the pump is not operating, there is no volume flow rate. So that's the HA, which we're trying to go through it. So information given to us. The drawings giving us the specification. The fluid is moving from this tank to this tank. This is an open to the atmosphere. So P gauge is 0. Velocity at the surface of this tank is 0. Pressure 0. And it goes to the center line. You have a fully open gate valve. You have the pump. And there are some stuff we need to consider here, like, for example, entrance resistance, the friction through the length of the pipe. We need to take that into consideration. And as well, you move for gate valve and the pump, and then the swing type check valve, and then butterfly valve, and then elbow 90 degrees, and the diameters for this pipe. So you have here a 3.5 inch schedule 40, and we learn how to get these values from our appendices from the textbook. I strongly ask you to go through our library and access the ebook because we have access to that. And it's saying to me there's a standard elbow and then going to that system. So there's a lot of things, but because this is a question, is a design in your scenario for your project, you will select the specification for your design and then you work around it and then you perform the calculation. So here, this system data and the values, the units, I set it up early and it's available for you to adopt that Excel file when you go and you find the assignment. So volume flow rate. So remember it's 850, so equals 850 divided by 60,000. So 60, it's converting it from minutes to seconds, and times 1,000, it's to convert the liters to meters cubic per second. And we'll give you that value, which is the Q volume flow rate. So I always write here the information is 850 divided by 60,000. So that way you understand where these numbers coming from. Okay, in case you want to know what's good. So 850 divided by 60,000. That's the Q. Put the Q in meters per second. So that way you understand where this number is coming from. All right. Pressure at point A. So we're taking point A in this here. This is point A. I prefer always when I work with this type of questions, I label my points, and that way the reader behind me or anyone wants to check my design will understand what I'm doing. So here is my point A, Control C, Control V, and here will be my point B. So you understand where is A and where is B. Again, this is me invented, so it's open to atmosphere. So the P gauge is reading for me is 0 at that point. However, Pressure at point B, as stated, tank maintain a pressure of 240 kilopascal. So 240, I don't need to put the times 10 to the power 3 because I have the unit set up in kilopascal. Velocity at A, because it's a big reservoir, we say it's close to zero. It's not zero, never been zero, because the fluid is moving, but we assume it's close to zero. Same thing here, velocity at point B is also zero. This is assumptions. We assume it just to simplify the solution. Elevation at point A, so the elevation we take always as the reference point, this one, the center line of the pump. So from the center line to the surface of the first point A, that as showing here is 2.4 meters. So I copy that value, but the elevation from the center line to point B is 2.4 plus 24.4. So I could write this equals 24.4 plus 2.4. And that way you understand this numbers where it's coming from. The 26 is the total of that value. All right, 26.8, this is the information given to us. As we say, velocity head. Now, velocity head, if you remember the equation for velocity head, it's the requirements for v square over 2g. So if I want to write this equation here, velocity head, I would just insert, I would just write it, v square over 2g. That is actually the velocity head. I would just make that subscript. Show you here how can you make that value subscript. You come here to the columns. First, we need to exit here. It's trying to, okay. I can copy this one to make my life easy. So we'll say v square over 2g. It's not letting me doing that, but try, because you could go to home, and from home you can change that to superscript, and that way will comes the v2 over 2g. So that is better. Yeah. The same thing for that one is v squared over 2g. Now, because the velocity is 0, so that will be the value. That is actually needs to be adjusted. Control X needs to come here so it can match the values. We keep that one just the same like this, so people will understand what we're coming with. Okay, so velocity, since it's 0, so that will be 0 divided by 0 squared divided by 2g is 0 and 0. Pressure head at point A, because the pressure at point A is 0, so that equation is, if you remember it, it's P over a gamma. And let's see, so gamma is specific weight for the fluid, and that where I'll put gamma so you understand this is the specific weight of the fluid. And that is kind of like what we need to be aware when to calculate the pressure. So if it was at point A 0, then here will not be 0 anymore. It has a value. But to do that, I need definitely to understand what is my value. And that's why we're trying to get this from the specific properties of the fluid. What is the fluid? Is water at 15 degrees Celsius. So I need to solve that. I need actually the specific weight or gamma for the fluid, and then based on it I can do that and to give it a pressure head between it. So I know the specific weight for that. I need to go to my appendix from the textbooks. Which appendix to go there? I'll tell you now. I'm just accessing the textbook from other monitor. Appendix A, so right there, fluid properties, put just the brackets, appendix A, properties for water at 15 degrees. And how can I get these values? Very soon, I'm just sort of organizing this. So that is fluid properties, Appendix A, properties for water at 15 degrees. I can see it. The specific weight is 9.81. So I put the value here, 9.81. And the kinematic viscosity, so that as well, I could copy it here, and then the people will understand what is gamma. So I put specific weight, and that way people, when they read this, they can understand what's going on. You can expand that so people can see it. And the kinematic viscosity, I need it for Reynolds number. And from that table, kinematic viscosity is 1.15 times. So I'll put it as equal. So it can be equation to E minus 6. That is kind of like to give me the value for it in the to the power minus 6. All right, so that is very good. Now I got the kinematic viscosity. To come to solve this equation, I say equals the 240 divided by the specific weight, which is gamma. And then you can see the number is giving me this value. So that will be here again. So specific weight, the pressure, if it's 0, divided by whatever specific weight is 0. But when it's P, so we will have that pressure at point B divided by the specific weight giving to us. And then from this equation, you get these value. Good. So we get the following for 15 water at 15 degrees Celsius from Appendix A from the textbook. That's why I recommend they use the textbook. Now, we come to the following information. Again, I need to access some textbooks for that because all these informations are really important to find the appendices for steel pipes, schedule 30. So the first one, you have 3.5 inch schedule 40. The diameter, I can get it. And also I can get the area from the appendix. So to go to that is Appendix F. So write comment here, Appendix F from textbook. And that appendix will give you dimensionless of steel pipe. The first one, we take the diameter. Make sure to take the internal diameter because that's what we're solving. For the first one is a 3.5 inch. So I'm in my textbook, the internal inside diameter. I take the SI unit system. If it's meters, millimeters in the textbook. So make sure to divide that by 1000. So 90.1. So it would be equals 90.1 divided by 1000. So I'm converting it from millimeters from the textbook. Now, the other things which I need to take for the 3.5 inch is that value equals 6. The area 6.381 E minus 3. Minus 3. Otherwise, it will not be negative. All right, so that is the area for the section line. This is the information for the section line, this information for the discharge line. You can call it, and that way you understand that. Okay, so now I got the same thing because I'm still on Appendix F. I could put this here as well. So people, when comes and see the information, they know where this is coming from. So now I have the 2.5 inch, the internal diameter 62.7. So it will be equals 62.7 divided by 1000. And the area for that, based on what is giving to me, is 3.09 E minus 3. All right, so I got this one and the area for each one of them. All right, so that is very, very important for us to get to work with this type of properties. Now, another things which I need to ensure to find is the wall roughness, E for commercial steel, and I assume it here is clean, so I need to go a special table available within the friction losses. So I'll tell you which chapter. So for that one, we go to Reynolds number, laminar turbulent flow and energy loss due to friction, chapter 8. From that table, actually, you can find the wall roughness, but you need to find it in meters. And I will work on that very soon. So it's loading up the textbooks. It's a bit to go through it. So you find that table. I think it was one of the possibly 810 the table, but I'm checking it now, so I can write the information for us when we go in the future. So that's the procedure you follow anytime you solve questions related to this type of application. Yeah, table 8.2. So I'll call it that one, table 8.2 from the textbook, the one we're talking about. And I will tell you which page is it. Is page 201. So page 201 from the textbook. So table A2 will provide me the relative, the roughness for steel commercial with the following value, 4.6 E minus 5. And that is because we're using the same commercial steel pipe. So will be as well 4.6 E minus 5. Right, but that one should be in meters, just to correct that, not millimeters, because this is the value I took from the textbooks is in meters, not millimeters. There was a typo here, I just corrected the units. Units are very important because based on it, we can solve this question correctly. All right, now the length for each one of them, we assume the length for the first one, it's just an assumption here from that point to this, to the pump, the length, we assume it's about 2.44. And the other length, it's for the other pipe. We take that with the question itself, 109.7. So definitely this is part of your design of the question. In your design question, you need to assume the lengths and take them into account to calculate the friction losses. So I'm giving you the values here for length for this from here to the pump, it's 2.44 meters. And from the pump, the discharge line to here is about 109.7 meters. Units are in meters, is very important. Now, E over D is a ratio. So we supposed to divide. So it will be equals E wall roughness divided by the length, and you get that value. Sorry, E over D. So I made a mistake. E over D. And this one would be here equals E wall roughness divided by D. Right. The other information, which is a ratio as well, will help me with Darcy equation. So that one will help me to calculate Reynolds number, the friction factor. Then this one will be the length we assume divided by the diameter. Make sure that's why I have the same units. And here will be equals the length divided by the diameter. So that would be useful for me for Darcy equation, L over D, and this one, E over D, relative roughness for Reynolds number. With Reynolds number will help me to find the F, friction factor. All right, flow velocity, here you have the Q. So to do that, I'll write the equation, continuity equation or volume flow rate equation equals VA, velocity times the area. So V rearranging that equation will be equals Q divided by A. And that equation will be for each one of them based on the area. So equals the Q, it's one value, which we assumed, or we took from 850, divided by the area for the section line. And you get about 2.2 velocity value. And we do the same thing here, equal for the discharge line, Q divided by what? Divided by that area for this one. All right, so now we got the velocities. If you don't like to see that one, just make it a number, and that way you can see the velocity is 4.58, and this one as well as a number, and that 2.2. Velocity head, as we mentioned it earlier, velocity head, I will copy this one. This is the velocity head before and after entering the pump. Now you say, hey, you say velocity, that was velocity head at point A, velocity head at point B. But now inside the section line, there is a velocity head and also velocity head at the discharge line. So that one, based on that equation, equals, open brackets, this value square, close, divided by we can 2 times 9.81 and close the brackets. So I just use that equation, will give me 0.25, and then I would do the same thing, brackets, this one, the velocity square, divided by 2 times 9.81. Here is very important for you to really be very careful with the what we call it, the board mass, how you arrange the equation. I'm just using them numbers because if you have like significant figures too much, you can change a bit of your results slightly. Reynolds number is calculated on following equation. Reynolds number is the rho V divided by rho VD divided by dynamic viscosity, or VD Reynolds equals VD divided by kinematic viscosity. Now, kinematic viscosity is the one we took already from the fluid properties for, we call it water. So it's good to have these handy for calculations. I'm just enlarging this so you can see. So that is velocity times the diameter, kinematic. Now I have two Reynolds numbers here. One is the Reynolds number for section line and Reynolds number for discharge line, because again, they don't have the same diameters, they don't have the same velocities. However, they have the constant volume flow rate, which is continuity equation. So Reynolds equals, based on the equation, velocity, not velocity head, velocity multiplied by the diameter, VD, divided by kinematic viscosity. You bring these cells, you get this value. Now, this Reynolds number, again, make it as a number. It's telling me it's a huge number, which is turbulent flow. If it was laminar, it would be just 64 divided by Reynolds. You get the F value, which is the friction factor value. Here, again, equals velocity, not velocity head, please remember that, flow velocity times the diameter divided by the kinematic viscosity. Again, this will be a turbulent flow. It's bigger than 2000. So when we know this is a bigger than turbulent flow, will be 2000. Now, from the same chapter 8, there are two methods to get the friction factor. One is you get it straightforward using Moody chart or Moody calculator. But also, as I told you, there is a method which the chapter is providing you with an equation, easy and ready to use, which I will just copy. I'm just trying to get it from the textbook. Friction factor to turbulence. So I will print screen that equation. So technically, for simple solution, we could use this equation. This equation is very simple and easy to set up into your what we call it Excel file, and that will give you the file. So equation 8.7 from chapter 8 from your textbook, definitely can embed that equation. I have here, instead of E over D, I have D over E. I need to be careful with that. So it would be the reciprocal of that. I could change that to be D over E and D over E to make it okay. And 1, and the log, make sure is log 10, and 7 for that. So I will type this equation. All right, so to set up that equation, you can see it here. I put the 0.025 divided by log 10 brackets. I use brackets as much as I can to make sure, because here was D over E, but my equation is E over D. So I put it on top. So 0.17 is the E over D, the kind of like reciprocal for that, divided by 3.7 plus 5.74 divided by Reynolds number for that one, to the power 0.9, and then close brackets, and then you get it that way, you get the value. So I did it now. I will try it here again. So that is very straightforward. I didn't need to go to Moody chart or Moody calculator. I can do it again. Equals. You follow the same example, 0.25 brackets. Put brackets as much as you can. So the first bracket is for the log 10, and it's recognized. Put the first brackets, and I put another brackets to make sure what I'm doing is just to work around the values, and if something wrong, I can fix it. So here will be E over D on top, because this is the inverse of that, divided by 3.7. Close that bracket. See the colors is changing. Plus, now open another bracket. So you have 5.74. So I'm doing this equation technically, and divided by Reynolds number, you go for that value to the power 0.9. Close the brackets. It's showing me now. I close this brackets for the log. Now, when you close the log brackets, you need to close another one to be to the power 2. And that way you can see my brackets close nicely. If I have extra brackets, the system will tell me. And then you can see I had it kind of like extra brackets, and it's helped me to fix it. So this was for this one, and this one was for this one. I think that's what I was thinking. Yeah, this one was for this one, and then this one was for this one, and then divided. Instead of mul 0.25, that should be divided, and that way will address the issue. And then you get it. So I got the value exactly what I anticipated. So it's just very simply, and if you want to show significant figures, you can bring it that way, and you show it to anyone in the way how you want to do it. So I got that from this equation. Usually I put this equation here so people can see it in a nice way, so they don't feel like, how did you get that from which equation? So it's from the textbook, equation 8.7, friction factor for turbulent flow. If it was laminar, it would be very simple. F equals 64 divided by Reynolds. Life is easy and simple, but in many usually in this type of examples, it's a turbulent flow. All right, so that's we did calculate all the important information for the suction line and discharge line. Again, because we have different diameters, different tube sizes or pipe sizes, we end up to calculate Reynolds numbers, velocity head for each one of them. Okay, now losses in section line. We have two type of losses. One is the biggest losses is due to the friction of the pipe. The second one is the losses due to what we call it, the minor losses due to fittings, such as you have, for example, interest resistance, you have gate valve, as showing you in the section line, discharge line, you have swing type check valve, butterfly valve, two standard elbows, and as well friction and possibly exit loss as well. So all of these things, we need to go through them one by one. All right, so we come with the first thing. Pipe, this is the, we call it the friction. So K is the value, which is in this example, it's using Darcy equation. So it's FL over D V squared over 2G. So what we do first, we find the K value, which is F equals, F is the one we calculated, multiplied by L over D, which we did initially. That's the reason I did the L over D, equals. That is the K. Quantity is 1. Total is that value should be multiplied by the energy loss. Energy loss is what? Is you multiply that, the total K, multiplied by the velocity hit. So O and 20. So it should be velocity head. Why velocity head? Because velocity head is V squared over 2G. And you get that value. So velocity head is that value, which is point, if you look to that cell, is 20 or 20. And if you come here, you can see I use or 20. So K times velocity head, V squared over 2G, that is the friction, and you get the units for that in meters. Now, we have interest resistance and we have gate valve fully open. Again, if you go to the chapter minor losses from the textbook, minor losses in your textbook, you have the following: interest resistance. I'm talking about chapter 10. I get some of the information here for you. So first one, entrance resistance. You will get that figure 1014. I'm just moving it here. And based on figure 1014, you will find that interest resistance, we could choose square edge inlet for that. So you have inward, I'll just zoom it up, Control X, Control V, so you can see it better way. It's better to go in the textbook, you can see it. So you have inward projecting pipe, square edge inlet, K is equal 0.5, chamfer inlet, and rounded inlets. The one we can see from the question, it's actually matching this one. So square edge inlet. So I would choose square edge inlet, which based on the chart is K is equal 0.5. So I would say 0.5. Minor losses, it's K times the velocity. How many are they? 1. And then very quickly, that equation is set up to be this value multiplied by V squared over 2G here, which should be giving us. So O27, like V squared over 2G. So that should be like that times that times the velocity head, and we give you this value. Sorry, I did the wrong thing. 0.5 and that one. So that is the correct one. So Q25 times the O20. So that is the value. I was just doing it here, but it's already set up here in the energy. So the total, which is 1 quantity times 0.5, that would be 0.5. 0.5 times the velocity head, 0.25, and then we give you 0.125. for the interest resistance. Now we have gate valve fully open. Again, from gate valve fully open, I just choosing for you something. So this is gate valve fully open, Control X, Control V. I'm just showing you some of the information. I got them from the textbook. It says you can use K8 for it. So gate valve, it's 8 FT. So I'll put the information here. It's K is equals KFT. Now you say from where we got this from figure 10 from figure 1017 and table, because we have a table for that as well. I got that table here, Control X, Control V. That table has all the information we need for our values. So if it's gate valve fully open is 8, the LE over D. And if it's the section line, as you know, it's 2.5 inches. So that will be 0.018. So that is table, we call it table 10.5.5. You get the FT equals 0.018. All right. So all this information, I'm showing you how to get them, but I'm also writing the comments here so you can see what you're going through. We come here, we say 8 times 0.018, and then I get this. How many are they? It's only 1. And then you get the value 0.14, and then we'll go through it. So sometimes you find some of the textbooks, they have different values, but I'm following exactly what's given in this table. I think there is slightly difference between the SI units tables and the other one, the edition 7. It's all based on experimental values. So again, to go back, we done all the information. So from the reservoir to the inlet of the pump. Now, we call this losses in section line. Losses in discharge line, so we will start from the pump till we go to the reservoir. So we have the friction through the pipe. Again, we could write this equation equals, so the K equals F times L over D. Is again different from the method, and then that is the K, resistance coefficient, and then you multiply that with the remaining values. So you come here, F, which one we taking? We're taking for the discharge line, this discharge line. This is the F we found from the calculations. Multiply by L over D, we already done in advance. Okay, the quantity is 1, total is that, so we'll be here equals, I would do it again, this value multiply by velocity height for the discharge line, and you get that value. Okay, we can make that so it can apply for all of them. We have another thing, is swing type check valve. Swing type check valve, fully open. Again, you can come to this table. Swing type check valve is 100 Fs, and because it's table, so we can write here it's 100 F, and from that table you get the value 0.018. But sorry, you go to this one 0.17, because now we're talking about discharge line, so that will be the value 7, 0.017, because it's 3.5 inch. Now I'm looking for, I got them in the opposite direction. Sorry for that. That should be 0.017, because it's 3.5 inches the section line, and this one is the discharge line is 8. So you need to be careful with those when we read them, but it's the same concept. So I need just see how nicely to correct that. I come here to this value, I say, hey, this should be 7, and then boom, automatically will update everything for me. So when I came here, it's 100 times 0.018. Now I tell you why, because I found by mistake, I took this as the section line, but actually this is the discharge line. Discharge line usually is smaller diameter than the section line. Section, you bring bigger diameter, 3.5 is 0.01, and then the other one 0.018. So that is what we got from chapter 10. All right, so the quantity is 1, and you get very quickly everything calculated in one go. 1.8, that should be this value multiplied by velocity head. To correct that, there was some miscalculations. All right, butterfly valve widely open as well. We will take that from the butterfly valve. You can see it here from table 10.4. So here we could adjust that. We say from table 10.4, and this one as well from table 10.4. So this is very helpful for you when you work on your assignment. And you can see that's the butterfly valve. It's fully open. It's about 45. So that FT and FT is the same thing. So I could copy this one and put it here as well. And I would say to solve that, the same equation would be equals 45 multiplied by 0.018, and you get 0.81. The quantity is 1. This will calculate. I will check that just in case this one multiplied, if in case something happened to my formula sheet, and you get the value. What's happened? This multiplied by this. Good. It's just an error. Sometimes happen. Now, another things would happen in this. We have exit loss. Exit loss is a special table we could find, which is this one. From the textbook, assumption for exit loss, section 10.4, read it. Exit loss: as a fluid flows from a pipe into a large reservoir or a tank, as shown in figure 10.4, its velocity is decreased to vary. So we assume the value exit loss K is equals 1. And you come, this has one value, 1 times 1, and then you come here, this multiplied by velocity head, and then you get the value. So again, everything we're saying where the information we're getting it. The last thing we have from this is elbows. So we come here to this section. Standard elbow 90 degree is saying we choose the value 30 based on this. And so I will copy that line again because that is very important information. So 30 FT. So we come here, we say 30 multiplied by 0.018, and then the quantity is 1. That will be just multiplying this with this to give you the right value, and then we just check it, multiply by this. Now, here is the trick. I made a mistake. Actually, they are not one quantity. The quantity is 2, 1, and 2. So when I correct that one, that is the right number. So you make sure the quantity is addressed correctly because you have 2 elbows. Now you come here, you multiply this times the velocity head, and you get the value 1.07. Automatically, this should add for you the total energy loss. So it's mean the total of these plus these, I'll rewrite this equation, equals sum of the following plus sum of the following. And then you get 42.28. That's the total energy loss. So added all these losses plus these losses, you get the total energy losses from the system. Now, to do that for calculating the other information, it's good to understand the total head on the pump, which is required by the system itself. you need to include with it the elevation, so you can get the right value. So we did put somewhere the elevation. So the elevation where you're trying to transfer it from point to another point, and how can you get it to go to the right direction, because kind of like you need to ensure your elevation is going correctly. All right, so to calculate the total head of the pump based on general energy equation, the equation is telling us is to calculate HA, rearranging the equation, which will be delta P, pressure head difference between B and A. So because A is 0, but B has a value, so I'll call it here, I'll show you the equation, will be 24, that's the pressure at B, plus the elevation difference, which is delta Z. So plus delta Z, which will be elevation, this value minus this value. So that is the delta Z, the elevation, which is represent 24.4, plus what the last thing we did calculate is this one, which is the total energy loss. So technically, total head pump required on the pump is about 91.14 meters. What is required to do that? By the way, if you don't make these significant figures, you may get an answer about 90 point something. So it's all by rounding numbers and stuff like that. So that is based on the equation which we apply in this type of applications to calculate the pressure head. So I'll write you the equation so you can see it, how this will work, in case you will be asking later, how did you get the HA? So it's technically by using this equation. So that is the last equation, which 24 is delta Z, 24.41. This is sometimes is different between instance, because if we round the numbers here, such as I rounded the velocities head and the velocities, you could get these type of differences between them, but it's not much difference in the design. All right, so that is just calculated the total head on the pump using all the requirements for it. So that is the first video. Now, next video, I'll show you how to select the efficiency of the pump.